Hi, I'm Sriram, and in this video, I'm going to describe my experimental project for implementing collective communication on mobile devices. In this experiment, I analyzed parallel tree reduction algorithms, understand synchronization overhead, identify key performance bottlenecks, and also verify a certain hypothesis of mine about CPU-GPU synchronization characteristics. The first hypothesis is that there must be a crossover point where GPU becomes faster than the CPU. For small problem sizes, CPU should win because GPU synchronization overhead is too high. And the experimental setup consists of a test matrix which has 10 problem sizes from n equals to 256 upon 12 million. There are two kinds of implementations here. One is a multi-threaded CPU and there's a GPU implementation. It's a controlled environment, the same algorithm, the same device, and warm-up is done both on CPU and GPU. The expected behavior is that CPU time is going to be nearly flat because it has only 8 cores. So, and because of that, the parallelization benefits are diminishing. The kind of limited, you have a flat time. The hardware stack, I have a Pixel 10 Pro mobile device. There's a system on chip design, so CPU and GPU exist on the same silicon die. The octa-core CPU has a big little architecture, which has heterogeneous cores. And the target GPU is a PowerVR DXT from Imagination Technologies. There's a unified memory architecture. The software stack consists of, you need at least Android 24 for Vulkan support. Vulkan is the official standard API for GPU access on Android devices. I'm using Android native development kit for C++ toolchain and libraries. I'm using C++ 17 and GLSL for shaders. I'm using three kinds of barriers in my project. The first being a GPU shared memory barrier, which performs a synchronization among threads within a workgroup. There's a GPU pipeline barrier that synchronizes across workgroups, that is between different stages of the pipeline. And then there's a CPU thread barrier, which is at the OS level on the CPU, and there's a context switch overhead involved, so it's a bit slower. I'm using a coalesced memory access so that threads can access consecutive addresses. A single transaction is enough to read the data. I'm implementing four shaders in my project. One is a vector add task shader that is just used in the very beginning to complete all my integration points. It's basically compute bond, embedded single parallel task. It's not much significance. And then there's a local reduce task, which does within a work group. There's a synchronization involved only within a work group. And to scale beyond the 56 elements, that is beyond a work group, you need a tree reduce algorithm. It uses push constraints to communicate with the CPU for some relevant information. This particular naive implementation comes with 13 passes, so there are 12 barriers involved. The optimized tree reduce algorithm, however, it reduces synchronization overhead by doing more work per single pass. So more about this later. And there's a warm-up run done every time to eliminate any kind of first run bias and give you a hot path performance. The timing methodology, I have two kinds of devices. So a CPU and a GPU both have support to record the timestamps. But the CPU side timing has been observed to be more reliable. The Power BI driver is returning to me some garbage values like zero or a particular constant value. So I just discarded it completely. With the results with the naive tree reduce algorithm, you can see that the CPU time has been consistently higher than GPU. So that means that this eliminates any possibility of crossover because 256 is the minimum possible value. And even there, GPU is much faster than CPU. So my hypothesis is invalidated. Another peculiar observation here is that the GPU time is being, both of them have been relatively flat, around 5,000 to 6,000, and not scaling up well. So, what could be a possible reason for that? This means that work is not taking up a lot of time. If work was taking a lot of time, the amount of time being taken by CPU and GPU would scale up. It's not scaling up, it's flat. So, that means the algorithm is synchronization bound here. So to optimize this particular algorithm for this task, you need to reduce the number of barriers, reduce the amount of synchronization happening. So the optimization would be to increase the amount of work per pass and reduce the amount of barriers. Here comes the optimized tree algorithm. You have only three barriers. This shows a 15% improvement in GPU time, which means our diagnosis was correct. And at different values of n, you have different trade-offs. For small n, optimized was working well, and for medium values of n. So the thing is, we have a more compute-intensive work group. Here, each pipeline stage is much more intensive, and because of that, the synchronization is heavy. and the performance benefits you're getting here are kind of diminishing. So they perform nearly the same. But for larger values of n, however, the optimized algorithm performs significantly and consistently better. So the takeaway here is that optimization is problem size dependent. Now you can see the results over here. CPU time has reduced drastically, and GPU time you can observe about a 15% improvement. Let's try to quantize our results as per Amdahl's law. Amdahl's law gives you a theoretical amount of speed up possible when you have a code with a serialized component and a parallelizable component. Uh, as per the different values I have observed during the experiments, I have made a rough estimate that 15% of the unoptimized code is serialized and 85% is parallelizable. That means the maximum speed possible is with infinite number of resources. That's about just 6.67. With the optimized code, however, there was observed to be only 3% of serialized tasks happening. So 95%, 97% of it is parallelizable. The maximum possible speed up is 33. So that means the optimized code can take good advantage of advanced hardware. It scales well. Key findings and observations are here. GPU is synchronization bound and it's not dependent on the work. This is just why the flat performance regions. The work is not the bottleneck, barriers are dominating the runtime. There's no CPU GPU crossover point on the mobile as per this experiment. So that means CPU overhead is kind of amortized across small values of n. So CPU should be slower. And for larger n, CPU parallelism works, but then GPU is much more parallel, so it's much faster. The hypothesis could have failed for the following reasons. The primary reason being that our hypothesis was flawed right from the beginning. I have assumed a kind of communication from between the CPU and GPU where there's a write operation from CPU to GPU and there is a read back operation from the GPU to CPU. But this is a unified memory architecture on this mobile. And because of that, GPU can read data directly from the memory. It does not have to depend on the CPU. And the CPU is having a high barrier overhead. There's a thread launch overhead as well. So CPU is slower. And GPU hardware barriers are much more faster. And now comes the CPU variability part where the OS is intervening a lot, and because of that, you can see CPU times have been a bit erratic, and also there could be a thermal throttling happening at different values and different points of time. There's a DBFS part contributing. The power supply here is not so rigorous as compared to the GPU, so it could be the CPU cores could be operating at different frequency at different points of time, and the CPU cores are in a big little heterogeneous architecture. So different cores have different frequency ranges, and because of that, there could be an inconsistency in performance. GPU has been performing consistently good because its frequency is fixed, the power supply is rigorous, so it's going to operate at the same frequency at all times unless there's a throttling, of course. There's no background task because this is a task specific. This is not going to be a general specific processor. Now, the second experiment is a iterative workload bottleneck where I have repeated the same thing 100 times in a loop. So it's a sustained task. The observation here is that the CPU reset is taking too much time. And the conclusion is that GPU optimization is not the only thing that you should be focusing on. There could be some CPU set data preparation that could be dominating your overall clock time. And now coming to the results, you can see here that the GPU task time is much lower than the CPU preparation time, validating our hypothesis that CPU thing should also be optimized. And also, if you observe, the GPU task time is here for a million value of n, it's much higher. It's about 36% slower. The possible reason could be there's a thermal throttling happening in the sustained workload, and because of that, the GPU is being slowed down. This is a more reliable estimate than having the isolated performance runs because GPUs are constantly being used, and its performance under sustained workloads is a more reliable metric if you want to measure. The project summary is as follows. GPU is decisively faster than CPU at all points of time. Workload is synchronization bound. CPUs are true bottleneck in iterative loops. And Pixel temper has a unified memory architecture. So your kind of optimization should be hardware aware. You should be hardware aware out of all times. And GPU native timestamp queries are kind of unreliable on Power BI driver. So in my upcoming experiments where I implement a different collective communication algorithm or perform a more rigorous analysis about the timestamps and other things, I should rely only on the CPU time, not GPU time. So that's all about my project. Thank you.